Hello students, welcome back. In the previous video we talked about linear dependence and independence concept and then went through some examples. Some of those examples were trivially simple like standard unit vectors, but if you have some arbitrary vectors, typically you'll have to set up systems of linear equations and then they can be highly unpleasant. But if you're a computer, that can be done rather easily, and that's what we did earlier on to establish algorithms about those kind of things. Okay, let's go over to a little bit more theoretical topic. Bases. Let V be a vector space, a linearly independent family of vectors v1, v2 all the way to vn that also generate the vector space V is called a basis. So we talked about the generators previously. A set of vectors v1 through vn generate V, or those are the generators, if every element of vector space V or every vector can be expressed as a linear combination. You see? Every vector can be expressed as a linear combination. Okay? And then also linear independence. So linear combination has to be zero, happen to be zero, then all zero. Should have been zero vectors there. Typo, sorry about that. Okay, let's look at an example. The standard unit vectors e1, e2, e3 all the way to en form basis. We call it the standard basis. So they generate, we saw, and that they are linearly independent. We saw that too. So we have it, basis. Okay, how about the next example? A family of vectors 2, 1 and -1, 2, 2, 1 and -1, 1 is a basis of R2. Okay, alright, let's do this. Yes, 3D examples are gonna be far more complicated. So let's do 2D example first. So in order to establish a basis, what do we have to do? Number 1, generate. Number 2, linearly independent. Both may take some effort. In terms of computation, I mean, they are not really hard. None of them is really hard here. Okay, which one shall you do first? Generating, okay, arbitrary vector AB can be written as x times 2, 1 plus y times 81, 1. And therefore A is equals to 2x minus y, B is equal to 1x plus y, and then can we solve for x and y here? Looks like it's not too bad. If I simply add these two up, then I'm gonna get a plus b. Oh, excuse me. Obviously I clicked some wrong key. A plus b is equals to, let's see, 2x plus x, so it is 3x. And then y will be gone, and we're gonna get x is equal to a plus b over 3. Okay, I have it here. And then how about y? Well, let's see. Shall I use this one? Shall I use that one? Oops. So b is equal to x plus y is equal to b minus x. That's equal to b minus this. And then this is equal to, let's see, 3b. So 2b minus a over 3. I hope my mental math is correct here. So we get this. A, B, arbitrary vector can be written as A plus B over 3, 2, 1. Let's put some space in between, just for aesthetics. And then y is this one, this number. And then -1, 1. So what did he do? For arbitrary vector, it is possible to get x and y, coordinate x and y, so that it can be written as a linear combination of these two vectors, 2, 1 and -1, 1. So generating, that part is done. So that part is done. It's just a skeleton, by the way. You may have to put in some more explanations in between if you want to be a little bit more perfect. Okay, that's done. And then let's talk about linear independence. Okay, alright. How do we set up? Linear combination x 2, 1 plus y -1, 1 should be equal to 0, 0. 0 vector. So what do we get? 2x minus y is equal to 0 from first coordinate, and 1x plus y is equal to 0 from the second coordinate. And then let's work it out. Oh, that's easy. Add them up, and then I'm just getting 3x is equal to 0. 3x is equal to 0 because if I add them up, negative y, positive y cancel each other out. I get x equal to 0. Good. X equal to 0, plug it into either this or that. Let's plug into the first equation. Now, second equation looks a little bit better to me. So x plus y is equal to 0. So 0 plus y is equal to 0. Y is equal to 0 as well. So what did you get? We have to have 0, 0. Otherwise, we are not going to get 0, 0 in the right-hand side, which means we have to have linear independence. So this is the computation related to linear independence, and here is the computation related to generating. Both were systems of linear equations, basically. Now, imagine you have to do this in higher dimension. Systems of linear equation, but this time we have 3D vectors. So you're gonna have equation 1, 2, 3, one for each component, and then we have 4 vectors. So you're gonna get coefficient x, y, z, w, and then you have 3 equations and 4 unknowns. Oh my! And you have to do some work so that it generates R3. Good luck. But this is not a basis, so which means you have to set up linear combination of x times this, y times that, plus z times w, put a linear combination, and the right hand side is 0, 0, 0. Get this linear equations done with appropriate method, and you have non-trivial solution. None of them is difficult. But to do all those with paper and pencil computation is huge pain in the rear end, I guess. Let me see, is there a better way to handle this through Mathematica? So let's begin with generating. Let's clear some variable. So, arbitrary 3D vector ABC can be written as x times 2, 1, -1 plus y times -1, 1, 0 plus z times 0, 1, 3 comma plus w times 4, 1, 1 and solve with respect to x, y, z, w, and this will generate non-unique solution. Let's see. Equation may not give solutions for all solved variable. Of course, there are infinitely many solutions. Y can be obtained by some constant minus 6 over 7x, so x is arbitrary. X is arbitrary, x is arbitrary. Yes, still, for appropriate x value, for example, x equals to 1 or even x equal to 0, we do have solution, at least one solution. So yes, generate yes. How about linear independence? So set these equal to this time 0, 0, 0, and then is there a non-trivial solution? And yes, x is arbitrary, so plug in x as non-zero value, say 1, then x is 1 and y is -6 sevenths, z is 4 sevenths, w is -5 sevenths. You can plug in x equal to 7 to get even all the integer solution. In any case, non-trivial solution exists, so not linearly independent. But actually doing those computation, as I did for 2D example, even that took a lot of time. It's not something you want to do, but well, I don't think this is appropriate for exam problem, but in homework I can write some 3D problem. Okay, how about this? The family of vectors, these two, is linearly independent, but it's not a basis. Okay, so in this case, linearly independent, but failed to generate. Okay, let's see if I can work it out with Mathematica. So okay, first generating a, b, c, that's arbitrary, x times 2, 1, -1 plus y times -1, 1, 0. So for x and y, because there are only two vectors, is this possible? And you see, no solution. So fail to generate. Okay, how about linear independence? Add up to 0, 0 vector, and then find out x, y. Do we only have trivial solution? Yes. Only x equals 0, y equals to 0 only. Otherwise, impossible. So linearly independent, yes. Generating, no. But then again, setting up all these equations and doing this by paper and pencil method, good luck about that. Okay, so much for bases and examples. Theorems and others, let's do those in a separate video.